My work group for semiconductors works on materials and semiconductor devices. An example is gallium oxide, a material for new high-power transistors, which are important for a sustainable energy supply for cars, ships, trains and airplanes. But sustainability doesn't concern only the objects of our investigation, but also the way we do the research, and we try to change our lab to a more sustainable modus. The most prominent semiconductor material is silicon, which you all know from the Silicon Valley. Silicon is a rather simple semiconductor. It has a cubic structure, and that means that the light velocity is the same in all directions in this crystal. The new, more modern semiconductors have a lower crystal symmetry, which means that the velocity of light is different in different directions, and this has a big impact on the properties of the material.
So at the moment we use a helium-cadmium laser from a Japanese supplier, which is a gas laser, so this means that it's very large. And during its lifetime it loses its power, so it has to be sent back to Asia for a refill. The newer laser is a new development by the company Coherent. It's based on a completely different principle, so it's a diode pumped solid state laser, which makes it much smaller and much more energy efficient. Our old laser contains cadmium, which is very toxic. The new laser is RoHS certified, which means that it doesn't contain any hazardous substances. So both lasers have the same wavelength and the same optical power, but the new laser draws 30 times less electrical power, has 60 times less noise, 60 times less weight, and 100 times less volume.
Our new laser is used for Raman spectroscopy. Raman spectroscopy means you shine the laser onto the sample, light is sent back from the sample with a little bit different energy, a little bit different wavelength, because you excite lattice vibrations. This is a very standard method to investigate materials, but if you apply it to the modern semiconductors with a low symmetry, where light propagates with different speed in different directions, it becomes a little bit more complicated. A number of years ago we have developed the correct theory to describe the Raman experiments in such anisotropic crystals. And this laser helps us to investigate materials such as gallium nitride, material from the metal gallium and nitrogen, and gallium oxide, material from the metal gallium and oxygen. And these materials shine back the light in a specific way, which now can be investigated and theoretically understood. The new laser simplifies our experiments, improves the results, and makes them more economic and sustainable.